Hello everyone, apologies again for that technical difficulties. So welcome to the types section of PLDI 2023. And we have a great lineup of speakers today spanning all sort of ranges of types from dependent type theory to refinement types to types for synthesis. So it'll be a good one. So our first speaker today this is a distinguished paper. Our speaker is going to be Ende from Waterloo. And he's going to be presenting some really interesting work on how you can take concepts from OO languages and use them to have good language support for reusable proof theory. And with that, Andy, you take it away. I hope.
Hello, everyone. So everyone can hear me, right? Okay. Hello, everyone. I am Ende. Thanks for joining me today for my talk about extensible metatheory mechanization via family polymorphism. This is a joint work with Amin and Yizhou Zhang. Expression problem is well-known and difficult problem to solve in language design. Say, we now write an interpreter in Coq. And we start with defining abstract syntax of lambda calculus using inductive type. Then we can write substitution function for it using pattern matching. We can also establish other metatheoretic results. Now we want to extend STLC. We want to add a fixed point construct to STLC. By adding the TM type, a new constructor called TM fix. Such simple addition to the abstract syntax requires us to duplicate the original code and proof. This practice is tedious and highly non-modular. In this scenario, we would dream of a reuse the existing code and proofs, and modularly add the new functionalities. In fact, this is a dream our paper aims to make come true. We introduce a new language design, FPOP. FPOP incorporates family polymorphism and OO idea into a proof assistant like Coq. Here, we have two families, base family STLC and the derived STLC fix. The base family STLC hosts the STLC metatheories, from abstract syntax to type safety theorem. Family STLC fix, derived from STLC, makes adjustments as needed by a fixed point extension. It adds new constructor to the inductive types and adds new cases to the recursive functions and induction proofs. Members of the base STLC family are automatically reused by derived family and need no adjustment. In particular, executing the last command, check STLC fix.typesafe, displays the type safety theorem of the fixed point extension. Although much of the type safety proof for STLC fix is found in the base family, FPOP automatically constructs a complete proof that satisfies Coq's checker. Moreover, derived families are readily composable for creating larger extensions that combine the functionalities of the individual extensions. For example, STLC fix pair is declared as an STLC extension that mixes STLC fix and STLC pair. In designing FPOP, we address challenges that arise due to the underlying language of a proof assistant being functional, dependently typed, a logic, and an interactive tool, all at the same time. Here, we introduce a new command, f-inductive, for defining extensible inductive types. Accordingly, we introduce two commands, the f-recursion and f-induction, for doing pattern matching and induction reasoning on extensible inductive types. Now that inductive types can possibly be extended, how do we ensure pattern matching remains exhaustive? The key idea is late binding. When we make the references to the f-inductive Tm late bound, we also make the references to the recursive substitution function and the substitution lemma late bound. For example, the name Tm is late bound, and thus the substitution functions refer to the Tm in their own family. Similarly, the substitution lemmas refer to the substitution function in their own family. Because STLC fix adds a new constructor to Tm, exhaustiveness checking requires the substitution function to handle the new case. This slide shows the 4 case handlers in the substitution function. Late binding makes it possible for the derived family to reuse the case handler without redoing the type checking against this motive type. Because Tm is late bound, that is, the meaning of Tm is polymorphic to its enclosing family. So, when the case handlers are inherited into the derived family, they remain well typed. Their types now refer to the Tm in STLC fix. Late binding allows flexibility, but it seems incompatible with having definitional equalities that a Coq programmer takes for granted when programming in a proof assistant. For example, we are proving a lemma about the substitution function. In Coq, we could simply prove this lemma by unfolding the substitution function. However, as we discussed before, substitution is late bound, and thus we lost the definitional equality on substitution, and we cannot unfold it. A key observation is that although late binding prevents definitional equality on substitution, it still allows propositional equality. fpop will automatically generate a propositional equality for each case handler defined within f-recursion. With the propositional equalities in a context, we can prove the substitution lemma. We just addressed a challenge on equational reasoning posed by late binding of recursive definitions. However, late binding of inductive types poses a related challenge. Let's say we want to prove disjointness and injectivity for the constructors of the Tm type. If Tm were not extensible, then the programmer could solve these two goals by simply invoking the discriminate and injection tactics. However, Coq's discriminate and injection tactics rely on the elimination principle Coq generates for an inductive type. This principle is incompatible with extensible inductive type. Our insight is that this eliminator Coq generates for inductive type is not only incompatible, but also an overkill for proving these two goals. FPOP provides for every extensible inductive type a partial eliminator. Partial eliminator weakens the standard eliminator with an option type. As we show in the paper, this weakened eliminator suffices for proving injectivity and destroyness of constructors. It is also compatible with late binding. To further streamline the proof, FPOP provides the tactics F-discriminate and F-injection. These tactics work by invoking the partial recursors FPOP automatically generates for extensible inductive types. A fourth challenge has to do with logical consistency. In a sense, the essence of family polymorphism is late binding, and the essence of late binding is self-reference. But self-reference might create cycles, and cycles could mean divergence and thus logical inconsistency. So to ensure consistency, FPOP disallows code reuse that would create cycles by enforcing the order of field declarations to be preserved by a derived family. FPOP is not just a language design. It also has an implementation. We implement a Coq plugin that compiles the FPOP features into Coq's module facility on the fly. This compilation conveniently reduces the trusted base of any development using FPOP to Coq. Every family member, that is, every field, is compiled into a Coq module, parameterized by self. This self parameter stands for the current family, and it also represents the typing context of the current family. And the programmer can interactively and incrementally navigate through a family using CoqTop. And this compilation happens when each field is defined. When a family is concluded, our plugin will aggregate those units into one standalone non-parameterized module. This translation is modular and efficient in that the code compiled for fields of a base family can be shared with derived family without recompilation. For example, all the compiled case handlers in family STLC can be reused by STLC fixed without recompilation. We apply FPOP to several proof engineering challenges. In the first case study, we extend STLC with 4 features separately: fixed point construct, product, sum, and iso-recursive types. The code base is ported from software foundations by peers and others. The linguistic nature of our approach allows us to retain a programming style similar to the original proofs in software foundations. These extensions can be freely composed as mixins to form new STLC variants. Such a feature composition often requires only a few lines of code. In the second case study, we mechanize abstract interpreters for simple imperative languages and also their sumness proofs. The code is organized into 3 families. The base family defines a generic abstract interpreter framework. It has a few extensibility hooks, such as the abstract domain and the concretization relation. Two derived families instantiate the extensibility hooks to perform type inference and constant propagation. Next, we talk about the metatheory. To formalize our metatheory, we formulate a core-dependent type theory. It extends the Martin-Löf type theory with constructs that can encode family polymorphism. We construct a proof-relevant logical relation and use it to prove logical consistency and canonicity. As of now, FPOP has two main limitations that seem to require more thoughts from the language design perspective. First is the restriction that recursion and induction on extensible inductive types need to be at the top level and cannot be nested. Second is that FPOP lacks supports for automatically converting terms along the generated propositional equalities. We look forward to addressing these limitations in the future. There is much related work in the space, especially on encoding, that address the expression problem. While the prior approaches are largely extra-linguistic, our solution is a linguistic one. It addresses the expression problem with new language abstractions. It allows for an idiomatic programming experience and is also likely more friendly to the novice programmer. To conclude, we have identified a language design and implementation that makes proof reusable using family polymorphism. And we welcome contributions and collaborations to further improve the usability, expressiveness, and applicability of the language. Thanks everyone for joining our talk.
Okay, thanks. Remember, if anyone has any questions, they can just come to this microphone right up front.
Hello? Yeah, very nice talk. My name is Jojo from Purdue University. I think your tool is really useful. Actually, I want to know if you can deal with this mutual recursive definition of the language. For example, in the A-normal form, people have the value and terms. They are mutually recursive defined.
Ende, can you hear us?
Well, the microphone directly goes to this book. He should be able to hear us.
Ende, you might be on mute.
I can hear you from YouTube, but there might be a lagging, so.
In the interest of time, I think we're going to move to our next speaker. Hopefully we can carry on this discussion over Discord.
Yeah, sure.